Okay, we'll finish up the test here with problems 18 through 23. 18 is about Arnold the Aardvark. He's flying up and down using his new jetpack. His position above the ground in feet at any time t, measured in seconds, is given by this function. And it wants us to find initially in part A, Arnold's position at t equals 1 second. Okay. So this just means plugging a 1 into the position function. And so what we get is 1 cubed plus minus 9 times 1 squared plus 40 is 32 feet. Position functions tells us where we are, in this case how high we are above the ground at any time t. Okay, the second question says find Arnold's instantaneous velocity at when t equals 2 seconds. Okay, so now velocity is the derivative of position. So v of t is equal to s prime of t. So I'm just taking the derivative of this function we started with. So this is just power rule. It's 3t squared minus 18t. Okay. Now we're going to stick the 2, because it's v of 2 that we want, into our velocity function. This will be 3 times 2 squared minus 18 times 2, which is 18, is just 12 minus 36. That's negative 24 feet per second. The next problem asks for Arnold's average velocity on the time interval t equals 1 to t equals 2 seconds. This is the type of problem we could have solved before we knew any calculus. An example would be we drove for 3 hours and we went 150 miles. What did we average? Well, 150 divided by 3 is 50 miles per hour. That's exactly what we're doing here. So we're going to take Arnold's position after 2 seconds and subtract where he was after 1 second. And then we're going to divide that by the time interval 2 minus 1, which is just 1 in this case. So his position at 2 seconds, we figured out just a second ago, that was 12. And it's down here again. I think we figured that out. Let me see. What did we do up here? We figured his position at 1. All right. So, and we'll have to get that in a second. So his position after 2 seconds, we're going back to our position function. 2 times 2, 3, 2 cubed is 8, minus 9 times 2 squared, meaning 9 times 4 is 36, and then plus 40. That gives us 12. His position after 1 second, we had figured out earlier, that was the 32. So we're going to do position after 2 seconds minus position after 1 second over the time interval 2 minus 1, and we get negative 20 feet per second as our average velocity. Notice that average velocity doesn't use the velocity function itself. That is instantaneous velocity. On this last page, we're trying to reason from this graph the answers to some of our questions. Your first question was to name all the values where f is not continuous. So we're looking for discontinuities, places that if we were drawing the graph, we'd have to lift up our pen, and we'd have to do that twice. Right here, the graph jumps from 2 up to 3, and then it continues along its way. So there's a discontinuity called a jump discontinuity at x equals negative 2. It comes to a sharp point, but it's not discontinuous there. And then over here, it has a hole in the graph. Now, whether that dot was above it or not wouldn't matter, because we'd have to come down here and skip over the hole and then continue on. That hole in the graph is referred to as a removable discontinuity. If I could just pull that dot down, it would fill the hole in. Or if the dot wasn't there, I could just put one there. If you can just fill in a hole, which basically means you're redefining a limit, then you have a removable discontinuity. Okay, so in answering their questions, the x values where it was not continuous on number 19 is at negative 2 and at 6. So those are our answers. Then we want to know where it is not differentiable, it being the function on the graph. Well, you need continuity to have differentiability, so these two have to appear again. The negative 2 and the 6 will be there. But you also have other places where graphs are not continuous. If you remember our earlier problem, vertical tangents, and also where graphs make sharp turns. This graph makes a sharp turn right here at x equals 1, so we add that to the list. The number 21, you can see the answer to it, and it says the limit as x approaches -2 minus means from the left side. So I'm coming in along the graph towards x equals, there's my x equals -2. I'm coming along the graph as my x values get closer to -2. My y values are getting closer to this point right here, which is at +2. And that was the answer to the question. Had it asked for the limit from the right, we would have been going up there to y equals 3 as our limit. The limit is a y value or a function value. 22 wants to know, is f prime the derivative positive, negative of 0? Is it positive, negative, or 0? Well, f prime of 0 would be the slope of the tangent line when x equals 0. So here's when x equals 0, and that tangent would have a negative slope. So the answer to the problem is negative. We also now know, and we didn't know at the time, that whenever a function is decreasing, falling left to right, that the derivative is negative. So in terms of what we know now, we know the derivative is negative, undefined, positive, 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 probably 0 somewhere up at the top there, then negative, then undefined, and then negative again. Finally, we want the limit as x approaches 6 of f of x. So that's where we have the hole in the graph right here at x equals 6. Well, the value of the limit does not depend upon the value at 6. It just depends on, is the graph from the right side approaching that dot and from the left side approaching that same dot, and it is. So the limit is the y value of that point, and the y value of that point was 1. So 1 is the answer to the last question. I hope these solutions helped. You might want to retry the practice problems and see how you do on those now.